Thank you for listening to my talk. My name is Craig Schroeder, and I'll be presenting work we've been doing on effective time step selection for explicit MPM simulation. The material point method is a method of simulation introduced into computer graphics for the simulation of snow, but has since proven useful for simulating solids, fluids, as well as a wide variety of complex materials, including the sand that you see here. As with most types of simulation, MPM can be simulated implicitly or explicitly. Implicit simulation is preferred when materials are stiff, whereas explicit simulation tends to be better when materials are non-stiff. Plasticity is particularly easy to implement within an explicit framework, and explicit is also easier to implement because nonlinear solvers are generally not required. Time steps are easy to choose for implicit because one can typically choose, for example, one time step per frame, relying on the implicit solver to keep the simulation stable. For explicit solvers, typically one uses a fixed time step that has been chosen by trial and error. In this work, we present a variety of time step restrictions that allow us to choose time steps automatically close to the line of stability without having to resort to trial and error. Most previous MPM work in computer graphics is implicit, following the original formulation of Stomopkin et al. These generally rely on fixed time step sizes chosen as a small multiple of the frame rate. By contrast, explicit MPM in computer graphics is relatively rare, with the 6 examples below being relatively prominent. With the exception of Feng et al., each of these either doesn't say how the time step sizes are selected, or the time step selection is based on fixed time step sizes. When implementing MPM explicitly, one tends to note that it's fairly common for instabilities to occur, especially when simulating fluids. These instabilities often occur when the configuration has largely gone to rest. It's important to note that simply choosing the time step size based on the particle velocities and the grid size is not sufficient for stability. This results in trial and error often being required to find a stable time step size. In this work, we present 5 time step restrictions, which work very well together and complement each other to keep the simulation stable. We note that for explicit simulation, we can do the time step using one time step size and then adjust the final state as if the time step had been something different. The cost of doing this adjustment is much cheaper than recomputing the time step. The first time step restriction that we used is based on the velocity. Namely, we don't want particles to move more than one grid cell per time step. We adjust this to take into account APIC. What matters on the grid is the velocities they would get at the grid locations, which will differ from the particle velocities by the affine portion of APIC. Below we see both the B formulation and the C formulation of this restriction. The second restriction is to go back and check to see if any particles move by one grid cell or more. This results in a quadratic equation for dt, which we'll need to solve in general in order to get our new time step restriction. However, we note that if the current dt already satisfies this requirement, then the quadratic equation can be avoided. Nice thing about this restriction is that it allows us to avoid missing collisions. Since particles can't travel more than one grid cell, they can't pass each other on the grid. The next restriction that we use is for the deformation gradient. The deformation gradient is updated multiplicatively. So the new deformation gradient is a perturbation of the identity matrix multiplied by the previous deformation gradient. We call this perturbation A, and we simply require that the elements be less than delta in magnitude. As with the positional case, this gives us a quadratic equation that must be solved. And as before, as long as the dt already satisfies it, we can avoid solving the quadratic equation. This avoids nearly all of the square roots in practice. This restriction has the added benefit that if delta is chosen less than 1/3, then it guarantees no inversion. That is to say, the determinant of f is guaranteed to stay positive. The main use of this restriction is to provide safety from collisions. Collisions can create arbitrarily large changes to the deformation gradient at the end of a time step. This in turn creates an arbitrary amount of potential energy, which can cause problems for stability in later time steps. By preventing deformation gradient from changing too quickly, we cause the time step size to be lowered when large collisions occur, allowing the simulation time to properly respond to large collisions and keep the simulation stable. The next time step restriction that we consider is based on the sound speed. This is a classical CFL restriction that occurs in the theory of stability for numerical methods for hyperbolic PDEs. This restriction simply requires that the numerical speed of information travel through a grid be at least as large as the physical speed of information through the partial differential equation. In this example, we have a vibrational test, which is dominated by sound speed considerations. Here, dark colors like black and blue represent relatively small velocities, whereas brighter colors like whites and reds represent very large velocities. The top left simulation is run using our CFL restriction. Here, a dt is selected that is approximately 0.0024. Increasing this slightly to 2.6, the simulation remains stable. However, increasing it even slightly more to 2.7, we get the simulation that starts to show instabilities. Namely, at the beginning, we get large velocities, which then later settle down. Increasing dt even slightly more to 2.9, we get a simulation that actually explodes. Thus, we see that these CFL restrictions are giving us time step sizes that are quite close to the actual line of stability. In the case of fluids, the sound speed is calculated from the pressure derivative with respect to density. This formula has been very long known in this computational fluid dynamics community and is widely used for the simulation of compressible flows. In MPM, it's more common to represent compression in terms of the deformation gradient determinant J, and so the pressure is more conveniently expressed as a function of J. This gives us the second formula on the right. In the case of solids, however, the sound speed is much more difficult to compute. The left two formulas are based on linear elasticity at the rest configuration. This gives us the formulas in terms of mu, lambda, and rho. Using the bulk modulus as an approximation, we get the formula on the top right. This is a formula obtained from the engineering community, which has then been adapted into computer graphics. But we note that this formula is only approximate. This approximation was used by Feng et al. For their sound speed calculations, which we evaluate below in these four plots. These four plots show the sound speed as a function of configuration for four different paths through configuration space. Red here represents the approximation used by Feng et al., and green represents the exact sound speed for that configuration. The first thing we observe is that there's relatively little relationship between the exact sound speed and the approximation used by Feng et al. In particular, the approximation by Feng et al. Isn't all that much more accurate than just using the rest configuration, which is denoted by blue. Note that the approximation used by Feng et al. Is exact at and near the rest configuration. In the second plot, we see that along trajectories that leave J fixed, the approximation used by Feng et al. Is in fact the same as the rest configuration. In the fourth plot, we see that there can be a very large ratio between the actual sound speed and the sound speed computed by Feng et al. We also note that this approximation can underestimate or overestimate the sound speed, and thus in Feng et al. A CFL number of 0.5 was used. This means that on average, they were taking about twice as many time steps as were actually required. Under some circumstances, Feng et al. Will underestimate the sound speed, and this can cause them to take a time step size that is too large, which results in instabilities seen here. One of our main contributions in this paper is the exact calculation of the sound speed. As far as we know, this has never been worked out in any community, including engineering. In order to work this out, we needed to assume an isotropic hyperelastic constitutive model. Here we've taken the singular value decomposition of the deformation gradient f, which gives us our singular value sigma. M here is the stress derivatives represented in diagonal space. We note that if an implicit solver is available, then it's also likely that M will be directly available as well. Otherwise, it's also convenient to express the sound speed in terms of the derivatives of the energy density. In the case of constitutive models like co-rotated or fixed co-rotated, the energy density is simply a polynomial in terms of the singular values. We note here that we are computing the maximum of a bunch of different quantities. Each of these quantities represents a different wave speed in the material. These wave speeds are exact. They are not approximations. The one we want is simply the maximum speed, which is what determines our CFL restriction. We note that oftentimes the maximum wave speed is obtained from a pressure wave, but this is not always the case, and sometimes the dominant wave speed is a shearing wave. In 2D, we observe two different types of wave speeds. The principal wave speeds, which are the ones corresponding to the formulas on the previous slides. The waves propagate along the principal directions. However, there are also other types of wave speeds, which we call quadratic because they're obtained as the solution to quadratic equations. This makes them a little bit more expensive to compute. In these cases, the waves propagate in directions that are a combination of two different principal stress directions. In practice, these are very rare. We observed only in about 3 cases out of 1 million tests that we needed to select the quadratic as the maximum. And in practice, we found that this was just not worth computing. In all of our simulations, we only used the wave speeds corresponding to principal directions, which are almost always corresponding to the maximum wave speed. In addition, in 3 dimensions, we have another type of wave speed that is a mixture of all 3 principal stress directions. We've never observed this to be the maximum wave speed, and its cost is otherwise infeasible to compute, and so we do not consider these types of wave speeds further. Please see the paper for more details on the actual derivation of these wave speeds, the types of wave speeds that can be formed, formulas for the quadratic version, and more commentary on how likely they are to occur in practice. However, at this point, we're still not done. This simulation is the same as the previous one, except now it's been updated to take into account the sound speed. One thing that's fairly clear from this simulation is that it's still not stable. In particular, as particles become isolated, they tend to become unstable. This led us to look at a single particle instability. To understand the single particle instability, we start with a single particle with a velocity of 0. The first thing that MPM does is it transfers this velocity and mass onto a grid, which gives us 0 velocities on a grid. Next, we need to compute forces. To calculate forces, we use the J stored on the particle. This gives us a pressure based on our constitutive model. This in turn gives us forces, which we apply to the grid. This gives us velocities on the grid that either are expanding or contracting based on the original J. Because the velocities are no longer 0, we'll have a non-zero divergence of velocity, which is used to update the J on the particles. These red arrows correspond to a feedback loop. If the time step size is chosen too large, this feedback loop may diverge. One observation we make about this instability is that it's actually relatively hard to detect most of the time. Because of conservation of momentum, particles follow a ballistic trajectory even when they are actually unstable, until the particle interacts with something, whether it be a wall or another particle, thus allowing it to release this energy into translational modes and fly across the screen. This means that often the instability is occurring before it is observed in the simulation. If we look directly at the update for j, we see that the new j is obtained as a scalar multiple of the old j. Because j corresponds to a pressure that is restorative, the j will tend to go towards 1, but it may overshoot 1 if the delta t is too large. And if the delta t is large enough, it'll continue to overshoot 1 and diverge. A simple strategy for preventing divergence is to require j to monotonically tend towards 1. The restriction that achieves this is shown on the right. Here, k is a constant that depends on the interpolation kernel that is used, and d is simply the spatial dimension. An alternative strategy that lets us take larger time step sizes is to allow j to overshoot 1, but to bound how much it's able to do so. In our case, we require that j continue to stay within the range between j and 1 divided by j. The tt requirement that achieves this is shown at the right, where here lambda is a constant that is computed off of the constitutive model. The first strategy has the advantage that it prevents oscillations. There's a monotonic progression of j to 1. Strategy 2 has the advantage that it allows us to take a time step size that is larger. For performance purposes, it's only really necessary to look at j near 1, since usually the fluids used in graphics are nearly incompressible. This means that the vast majority of the time j will be very close to 1. Under these situations, strategy 2 lets us take a time step size that's approximately a factor of square root of 2 larger, which is effectively optimal if the single particle instability is to be obeyed. Using this additional time step restriction allows us to get stable simulations for fluids as we observe here. Note that when particles become isolated in this simulation, they do not become unstable. Now let's take a look at some of the results that we obtained in this work. This is a simulation with fluids. The fluids splash around, particles become isolated, but because of our single particle instability, the simulation remains stable. The time step restrictions also work well in the case of solids. In this case, we have granular materials which collide with the ground, and again, they remain stable with automatic time step selection and no need to tune parameters. In this simulation, we have scaling to more than 1 million particles. We have solids with lots of collisions. Objects collide with each other, they collide with walls, they collide with fixed objects. The deformation gradient time step restriction allows the simulation to remain stable during these collisions by allowing advanced reduction of the dt before energy starts to grow very wildly. In this work, we presented 5 different time step restrictions which work together in order to provide stable time step sizes. Our method does not require trial and error or tuning of parameters to get stable time step sizes, and no other utilities are required other than time step size selection to maintain stability. We don't need to use damping. We don't need to mix APIC with RPIC. In this work, we relied on the idea of studying instabilities that occur in actual simulations, finding out the causes of the instabilities, and turning these instabilities into time step restrictions that allow us to prevent those instabilities. We note in this work that we have not obtained a guarantee of stability. MPM is very highly nonlinear, and guaranteeing stability in the general case would be very difficult to do. We also note that our solution to the single particle instability is derived in the case of fluids. Solving this in the case of solids would be more difficult because rather than bounding a single scalar, we would have to bound a matrix, namely the deformation gradient. Our derivation also does not take into account interactions with APIC. However, in practice, we found that the PIC version was sufficient to maintain stability even with APIC. We'd also like to look into other means of finding instabilities such as von Neumann analysis. Thank you for listening and I hope you enjoyed the talk.